Before I go through these examples, I want to go over some concepts that we'll be using over and over. We're going to be using relative acceleration, so it'll be a of b equals a of a plus a of b relative to a. So you go through the problem and you write down everything you might know about point B's acceleration and point A's acceleration. What I want to talk about is acceleration of B relative to A, where both B and A are on a rigid body. So here we have a rigid body, and we have point A and point B. I'm going to draw a line between those two. So I've told you to interpret that B relative to A on a rigid body means B spinning around A, because it's a rigid body, and so B cannot be getting closer to A. So the only motion relative is B spinning around A. So when you see A of B relative to A, I want you to think B spinning around A. Okay, so that's what I want you to think. And so first of all, I want to write down what these things are in general for polar coordinates. So if you have, that's the origin, and that's B, and let's call that R, and let's call that theta. We know from particle kinematics that this acceleration here is R double dot minus R theta dot squared, which is the same as V squared over R. But since a positive direction for R is outwards, we have to put negative because the centripetal acceleration is always in. And then this tangential or theta acceleration was R theta double dot, and this weird cross between R dot and theta dot. And as the R dot changes and the theta dot is changing together, that causes an acceleration. We went over that earlier. Okay, so first of all, on a rigid body, so we don't confuse this polar coordinate for particle movement with the rigid body, what we do, we change theta double dot, we call it alpha, and that reminds us that we are looking at a rigid body, and to R dot, and instead of theta dot, we'll call it omega. So that makes this one R double dot minus R omega squared. Okay, so it's the same thing. We're just saying that theta double dot is alpha and theta dot's omega. Alpha is similar to X double dot, so it's a Greek A. Omega is not a Greek V, but you're just going to have to remember that. It's just traditional. Theta dot is omega. Okay, now what we want to do is then do this for a rigid body. So for a rigid body, back to what we were doing, A and B, okay? A and B are not getting any closer together, which means that R dot is 0 and R double dot is 0. So that means this one here is just R alpha, and this one here is just minus R omega squared, but I'm going to draw it in the correct sense, going in, and I'm going to do R omega squared. So whenever you see B relative to A, this is what you need to think of. Just think in your mind, B spinning around A, which means an R alpha tangentially, and I'm assuming alpha is positive counterclockwise, and then an R omega squared from B pointing back to A. Okay, so now that we understand relative acceleration for rigid bodies, let's look at this problem. So here we have point A and B, and just like I did earlier, we're going to do A of B is A of A plus A of B relative to A. And the reason I knew I was going to do this is it's asking for what is alpha A B. And I know that's involved in the relative acceleration of B to A or A to B. So let's write down everything we know about these accelerations. Well, we're given that the acceleration at A is 5 meters per second vertically down. We notice that point B is rolling on the ground, so it has a horizontal acceleration, and the ground is not curved, it's flat, so there's not going to be a v squared over r or r theta dot squared, so we know the acceleration of B is horizontal with an unknown value. And then finally, I've told you when you see A of B relative to A, you need to think in your head B spinning around A and everything that means. So here I've drawn B spinning around A. So B spinning around A has, assuming alpha is counterclockwise, just alpha times r, and the radius is 5 meters. And you have the centripetal acceleration going inward from B to A of r omega squared, so 5 omega squared. So we're going to need to know omega to solve this problem, but we can get omega using instantaneous center. So if we now turn our attention to velocities, here is bar AB. We know that the velocity of A, we're given that the velocity of A is 6 meters per second down. And again, B is horizontal on the ground, so we know the velocity of B is horizontal. And so this is one of those problems where you're given two velocities, and you need to find an instantaneous center. Well, you draw perpendicular to your two velocities, and where those perpendicular lines meet, that will be the instantaneous center. So that happens to be this point right here. And by looking at the picture, I notice that that distance is 3 meters. So we have that omega of, let me write in the letters, that's AB. Omega of AB will equal V over R, or V of A is omega AB times the radius from the instantaneous center, which is 3 meters. So I just went ahead and solved for omega, which is the V over omega. So I have 6 over 3. So omega A is 2 radians per second. So I'm going to rewrite everything we know about the accelerations. We know that B has a horizontal acceleration, unknown value. We are given the acceleration of A is 5 meters per second down. Okay, and then B relative to A is B spinning around A, so it's R, which is 5, times this unknown alpha AB. And this one, the centripetal was r omega squared. R is 5, and we just calculated that omega is 2. So 5 times 2 squared is 20. So 20 meters per second squared, pointing from A back to B. Once we have this picture, all that's left to do is take x and y components to solve for the unknowns. And so I noticed that the unknowns are AB and alpha AB. They both have x components, but only the alpha AB is in the y direction, so I decided to start with the y components first. So taking the y components of everything in the picture, there's no component y there. This is minus 5. Okay, so that 20 going up to the left, the y component is 4/5, so it's going up. So 4/5 times 20, which is 16, going up. And the 5 alpha b, the vertical component is 3/5, so 3/5 of 5 alpha b is 3 alpha b. And so we get minus 5 plus 16 plus 3 alpha b equals 0. Or we get 0 equals 11 plus 3 alpha b, which just gives alpha b is minus 11/3. This negative sign here means my initial guess of counterclockwise was incorrect, so the correct direction is clockwise. So now I'm going to take the x components. So the x component on the left-hand side is just AB. It's horizontal. There's no x component of that. So the 20 meters per second squared is going to the left with an x component of 3/5, so 3/5 times 20, which is 12, with a negative sign going to the left. And the 5 alpha b, which we now know alpha b, is to the right, 4/5 of 5 alpha b. But remember, alpha b is actually going to the left, so I have to put in that negative 11/3. And so when you add that all up, you get minus 26.7 meters per second squared. And that negative sign means my initial guess to the right is wrong, so it's going to the left. So here's another problem using relative velocity and relative acceleration. So they're asking for us to find the velocity at c and acceleration at c. So those are both going along that 3, 4, 5 triangle. And so I'm going to start with the velocity. At first I thought I might try and find an instantaneous center, but I got intimidated and I didn't do it. But I'll try and solve it using an instantaneous center later. So I'm just going to use relative velocity. So everything I'm going to use VC equals VB plus VC relative to B. So everything we know is that the velocity of C is going down at this 3, 4, 5 angle. Velocity of B, since it's swinging around A, and it's going counterclockwise at 4 radians per second, is going to the left at a radius of 2 times 4 radians per second, or 8 meters per second to the left. And the velocity of C relative to B is C spinning around B. And so we need to know that length. So I did 0.5 squared plus 2 squared square root. And so the length from C to B is 2.062 meters. And at 90 degrees to that, the velocity is going to be this length times omega BC. So writing all this out, we have the velocity of C, which is, I've assumed, going downhill at 3, 4, 5 right here, equals velocity of B, which we know is 8 meters per second going to the left, and the velocity of C relative to B, which I'm assuming going down and to the right at this 1 to 4 pitch that's given by the geometry there. And it's L times omega, and we figured out the length of that length was 2.062 meters times the unknown omega. So we're just going to take x and y components, and we can get VC as well as omega BC. So the x components are 4/5 of VC, so minus 0.8 VC to the left, minus 8 to the left. And it turns out if you take 2.062 omega BC times the cosine of that angle, you get exactly 2 omega BC. Taking the y components, we get minus 3/5 or 0.6 VC going down here. There's no y component to VB. And then if you take sine of that 14.04 degrees times 2.062, you get exactly 0.5. So minus, because it's going downwards, 0.5 omega BC. Now, these exact 2 and 0.5 are not coincidences. Let me illustrate that. Okay, the reason we get exactly 2 and 0.5 there, let me redraw BC. So here's BC, and so there's B, there's C, and remember it's going at 4 radians per second counterclockwise, and this distance here was 2 meters, and this distance here was 0.5 meters. So, it's not going at 4 radians per second, it's going at omega BC, unknown omega BC. So, I'm sorry, let me write that, omega BC. So, the x velocity, this velocity here, it turns out you can just take omega times the perpendicular distance, which is 2 meters. That's why it's 2 omega BC. And the y velocity going down here is just the perpendicular distance, which is 0.5 times omega BC, and going downwards because it's spinning around BC. So you can do that. You can just take omega times the perpendicular distance, and it'll give you the components. And that's why these two numbers turned out to be 2 and 0.5. So at any rate, we end up with these two equations here when you plug everything in and put all the unknowns to the left and unknowns to the right. And I just plugged that into my calculator, and I got VC was 2.5 meters per second. It came out positive, which meant I guessed the direction correctly. And omega BC was 3 radians per second. And again, the number came out positive, which means I guessed correctly counterclockwise. So that means that VC is 2.5 meters per second going downhill. And also means, which we'll need later, that omega BC is 3 radians per second counterclockwise. Okay, so let's move on to the acceleration. So we know that the acceleration of c is also going downhill at this 345 angle. And point B, so if you look at point B, let me draw it again. So here's A and B. So we're given that the alpha for AB was clockwise at 5 radians per second squared. So that means the tangential acceleration is alpha times r. So alpha was 5, r was 2, that comes out to 10. And since it's going clockwise, B is accelerating to the right. We also have the r omega squared going downwards, and we were given that omega was 4. Again, the r is 2. And so 2 times 4 squared ends up being 32. And it always points towards the center, so in this case, B to A is pointing downwards. And acceleration of c relative to B, again, means c spinning around B. So here's point B, here's point C. And so you have, assuming alpha's counterclockwise, you have alpha times L, so the unknown alpha, and the L we determined earlier by Pythagorean theorem was 2.062 meters. And we have L times omega BC squared pointing towards the middle, so C to B is going this way. And L again was 2.062 meters, and we had just figured out, we needed this, we figured out omega BC was 3 radians per second times 3 squared. Okay, so we just take the x components and y components and solve. So the x component of AC is minus 0.8 AC to the left. Alpha squared r is 10, pointing to the right. This L omega squared, so 9 times 2.062. When you take the x component of that, it comes out to be exactly 4.5. And then this 2.062 alpha BC times the cosine of 14.04 degrees comes out to exactly 2 alpha BC. Okay, so now taking the y components, the y component of AC is pointing downwards, so and 3/5, so minus 0.6 AC. There is no y component to this alpha r, and r omega squared is pointing downward, 32, so minus 32. And if you take this 2.062 times 3 squared, and you take the y component of that, you get exactly 18 if you carry out all the digits. And if you take 2.062 alpha BC and you take the y component of that, it's pointing down and you get exactly minus 1/2. So again, I put all the knowns to the right-hand side and all the unknowns to the left, plugged it into my calculator, and I got AC was 12.97 meters per second squared. So I got positive, so the guess was right. But for alpha BC, I got minus 12.44 radians per second squared. It didn't ask for that, but in case it did, that means the original assumption of counterclockwise was wrong, so it's actually going clockwise.